Welcome back to calculus. We have so far learned about local optimization, finding the local maxes and mins and things like that. But if you're doing any sort of real-world optimization situation, you probably care more about global optimization, right? You don't care if there's a little dip. You want to know where overall is the minimum of your function. So yeah, we're going to move on and talk about global optimization. After we know about this kind of in the abstract, then we'll get to do some more application sort of stuff with it. But we really want to understand this well because, well, it's math class. We like understanding mathematics, right? Okay, so first we'll start with the definitions. These look a lot like the definitions for local max and min. So we say a function has a global max on the interval I. So this part is very important. We usually specify where we're looking for the maximum or the minimum. That could be the entire domain of the function. It could be the entire real line, but it's always good to be precise and say we don't just have the global max, or sometimes we do, but it's usually better to say we want it on some interval. But again, this is not just near a point, okay? And then the rest of the definition looks the same. So f of x has a global max at x equals c on the interval I if f of c is greater than or equal to f of x. So that's the maximum, right? This is what tells you we're doing a maximum. The function at that special point is bigger than the function anywhere else. But notice that in the local maximum definition, this inequality only had to be true for x near c. That's what made it local. The global part is now it has to be true for all x in the interval. Okay, so if you think of the interval as maybe like the entire domain of the function, this would be f of c is the biggest that the function ever gets, ever, for any possible inputs. Okay, and then similarly for the minimum, the only difference with the minimum is that now we have a less than or equal to. So the function at our special point c is smaller than the function anywhere else, at least on that interval. Okay, so one other note about vocabulary while we're here, we say that the maximum is f of c, or sometimes we call that the maximum value of the function. So whenever you see value, you want to think like the output. Okay, and when we talk about the maximum of the function, that's the output of the function. So that's like the value on the y-axis. We say it occurs at whatever the x is. Okay, so just be careful that you keep those two things straight. You don't want to say, oh, the max is x equals 3. That doesn't actually make sense. The maximum is whatever the output of the function is, not the input. And let's look at an example here. So what if we look at, how about like, well, let me call it f of x. F of x equals cosine x. So we understand this function very well. We've studied trigonometry before. Looks like this. We know that this is positive 1, and this point down here, I guess that's down there, is negative 1. And what's the maximum? What is the maximum? Well, the maximum is 1. Okay, so I can say, so let's say I is, so that's the interval where we're looking for the max. Let's say that's maybe 0 to infinity. So for all positive or 0 inputs, so for all non-negative inputs, what's the biggest that the cosine function ever gets? Well, we'd say the global max is 1. This number right here. So it's a number on the y-axis. Now you might notice there are several places where that maximum occurs. Those are all supposed to be the same height. I guess, wow, my graph is really bad. Let me try to redraw that. Something like that. That's also bad. Hopefully you get the idea. Those are all supposed to be the same height. At any rate, the maximum is 1, but it can occur at several different places. So if you remember your trigonometry, this is 2 pi. That would be 4 pi. The next one would happen at 6 pi. So there's only one maximum for the function. A function cannot have two different global maxima because the maximum is the output. And if there were two different global maximums, then one of them would be bigger than the other if they're different, right? One would have to be bigger than the other, and that would be the actual global maximum because the other one would be one of these possible x's. But the global max can occur at several different places. So there might be several inputs that all give you the same output, and that output is the single global maximum. So the maximum is 1, and it occurs at x equals 0, x equals 2 pi, 4 pi, ... So you could write some fancy notation for that if you wanted, but let's not worry about that. And then similarly with the global min, the global min is -1. And that, again, occurs at several places. So that's going to occur at x equals pi, 3 pi, 5 pi, and so on. So that's these points here. Okay, so just be aware of that. A function only has, or can have at most, one global max and min, because that's talking about the output of the function. The max is the output. But these can occur at several places. Let's just say at multiple places. Or wait, maybe be more specific. Multiple x values. Or of course, if your function is a function of t or some other variable, multiple whatever inputs. Okay? Okay. So the weird thing about global maxes and mins is that some functions just don't have them. So it's actually a property not only of the function, it's really the combination between the function and the interval on which you are looking for the maxes and mins. So for the rest of the video, I just want to draw you some pictures and show you the different possibilities of what can happen. So this is always going to be the x-axis, and then this will be the graph of y equals f of x, even if I don't write it for later ones. So let's say we have something like this. Let's say the left endpoint is a, the right endpoint is b, and I would say here I equals, so the interval I'm looking at is the interval from a to b, and notice that this interval includes a and it includes b, and I have these closed dots on the ends. Okay, so take a moment and try to think in your head, where do the global max and the global min occur? Okay, I didn't give you any y values, so we don't really care in this case what the max is, but where do they occur? Okay, so if I'm looking at this, I see there are several local minima, right? So there's local mins here, and here, and here, but only that one furthest to the right, let's call that x equals c. That's actually the smallest the function ever gets. So I would say the global min occurs at x equals c. And the global max does not happen at one of these peaks. So if you're just taking the derivative of the function and setting it equal to 0, you may never find the actual point where the global max occurs, which is a, right? Because maybe the function actually goes on past this, and the derivative at a is not 0. But because that's the endpoint, you can have a maximum there. So the global max occurs at x equals a. And just notice that occurs at an endpoint. Whereas the one at x equals c, that is a local minimum. Right? If you were taking the derivative setting it equal to 0, you would locate that x equals c, but you wouldn't find x equals a necessarily. Okay, so let's look at another example. How about this one? So maybe our interval is 0 to infinity. And my function is maybe something like e to the minus x, where it goes like that. Okay. Well, it is pretty clear that the global max occurs at x equals 0. So no problem there. But what about the global minimum? So let's assume that the x-axis is a horizontal asymptote for my function, and that means that the function gets closer and closer to 0, but it never actually gets there. So there isn't a global minimum. This function has no global minimum. So that's definitely a thing that can happen. Your function does not have to have a global max and a global min. In the first example, it did. I drew up an example where this one over here, this guy, does have a global max and a global min. Great, sometimes that happens. But sometimes you might not have one. So it seems a little weird. Couldn't you call 0 the global minimum of the function? So over here, I mean, there's y equals 0, and the function gets really close to 0, right? But we can't call that the global minimum because of the definition of global minimum. So we say, it has a global minimum at x equals c if f of c, but what number are you going to put in to get 0 out of your function? It just never happens. You can't plug in infinity. I mean, there are maybe some fields of mathematics where you say, oh, this has a minimum at infinity or something, but we're definitely not going to do that. And in real world applications, you don't want to say, I've got a minimum at infinity. Infinity doesn't often occur in the real world. So we just say there's no global minimum because the function can keep getting smaller and smaller. So any x you put into the function, there's always going to be other places where the function is smaller. You just have to go further to the right. So that's definitely a thing that can happen. And I will tell you the problem here is because we have an infinity on the endpoint of our interval. So that having infinities in your interval, if your interval doesn't stay within some like a to b, then things can happen with horizontal asymptotes and you might not have a max or a min. And we could also make a function without a global max, right? We could just flip this picture upside down. Maybe we go like that. And now there's no global maximum, but there is a global minimum. Okay, so yeah, that's a little weird. What other weird stuff could happen? Well, what if I don't want to have an interval that goes off to infinity? I mean, that kind of seems like cheating, right? Well, it's not cheating, but is that the only bad thing that can happen? If I don't go off to infinity with my interval, do I have to have a max and a min? And the answer is no. So let me draw you another picture. So now let's say I is the open interval from a to b. And we've just got a really simple function. It's just a straight line. Straightish, whatever. So what happens to happen at the endpoints? Well, the function can't be defined there, right? We're only talking about an open interval, which means we're not including a and b. So in the graph, I'm going to have to put open circles at a and b. And now let's think, what is the maximum value for the function on a to b? Well, you could say, well, maybe I just put in a point really, really close to a, but no matter what point you put in really close to a, you can always get a little bit closer. And then once you have that point, you can always get a little bit closer. And that's the thing about open intervals. You can get closer and closer to a, and no matter what interval, what number you pick that's actually in the interval, you can always pick one that's a little bit closer to the end. And when you pick points that are closer to the end, the function gets a little bit bigger. So there is no global min and no global max for this function. And I mean, maybe it's tempting to say, well, f of a, or whatever that value is, maybe this is like the value 5, and this is the value 2 or something. And it's tempting to say that, well, 5 is the maximum because 5 is bigger than any of the function values. But you can't say f of a equals 5 because f of a is not defined. We're saying the domain of the function is only the open interval that doesn't include a. So there's no point you can plug in where the function at that point is bigger than the function everywhere else. And 5 is an upper bound for all the function values, but it's not an actual function value itself, so that doesn't count as a max. Okay, and the same with the min on the other side. Same principle. So you could have a function where your interval is nice and bounded, it doesn't go off to infinity, there's no horizontal asymptotes, but you still don't have a max or a min. Okay, so now you're like, well, okay, well, I mean, come on, right? Look at it's the circles on the ends. That has to be making a problem. So what if you have to restrict yourself to an I? So let's say I is the closed interval from a to b where we include the left endpoint with a square bracket and we include the right endpoint with a square bracket. So none of that parentheses crap, no open circles on the ends. Can you make a function that it does not have a global max or global min, or does your function now have to have a global max and min? So take a moment and try this. See if you can draw a function that does not have a global max or min, or convince yourself that it has to have a global max or min. Go ahead, I'll wait. Okay, so presumably you pause the video and you've figured everything out. Here's my example. So it does not. You can actually draw a function that does not have a global max or min here. So here's the one I picked. I said we've got a nice closed dot here, we've got a nice closed dot here, and then my function looks like this. Jump discontinuity. Yeah. So, does this function have a global maximum? No, it does not, because it keeps getting closer to whatever that value is there on the y-axis. So let's say this is 10 or something, and this is maybe 3. The function's values get really close to y equals 10, but there's no number you can plug into the function to make it equal to. Oh, sorry, we're supposed to be defined on the interval from a to b, aren't we? So let's put a dot there so that f of c is actually defined. But f of c is less than 10, right? And f of any number is less than 10, but 10 is not a maximum because it's not an actual function value. And 3 is not a minimum because it's not an actual function value. So again, we have no global max. And we have no global min. Now there is actually another way to make this occur as well without having a jump discontinuity. You could also have an asymptote. So that might have been the example that you figured out, and that would be totally fine as well. There are a couple ways you can break this. So maybe we have a function that goes like this. Something like that, where this is a vertical asymptote on the left. So here again, I is the closed interval from a to b. The function is defined everywhere on that interval, but there is no global max and no global min. Okay, cool, right? A little bit weird, but you know, that's kind of how these things go. So it looks like the interval can be the cause of the problems. Like in the second example up here, it's really that this interval goes off to infinity. That can cause problems. If you want to have global max or min, I think of that as kind of a problem. Or if you have an open interval, that can cause a problem because the endpoints aren't included. But even when you do have a nice interval where you do include the endpoints and it doesn't go off to infinity, you might still have a problem. But notice that those last two functions, the functions for this example and this example, the functions are not continuous. So what if we have a continuous function and the interval doesn't have any problems? So the interval contains its endpoints, you don't get those open circles on the end, and the interval doesn't go off to infinity. And your function's continuous. It turns out that in all those conditions, if all those conditions are true, then you have to have a global max and a global min. And that theorem is really, really important. It is one of the big three in differential calculus. So this is called the extreme value theorem. Super extreme. But extreme value just means max or min, right? The extrema. So this is the extreme value theorem. And it says this: if f of x is continuous, and we already saw the continuous part is very important, it's continuous on the interval from a to b. Notice that I am putting square brackets on here. Okay, so notice this is closed and bounded. Then f of x must have a global max and min on a to b. Must have a global max and min on the interval. Okay, so when I say an interval is closed, I mean that it includes the endpoints. Okay, so closed means it includes the endpoints. And bounded means it does not go off to infinity. Or minus infinity, of course. So if you have a regular old interval, includes a and b are not infinity or anything weird like that, then your function has to have a global max or min. And if you were doing some optimization problem, you're trying to like find the best way to build your rocket ship, it's really nice if you know that your function has a global maximum before you try to find it, right? If your function doesn't have a max, then it makes it a lot harder to do the search for a max, because maybe you'll never find one. So it is really, really useful to have this theorem. I know that in the past I have said we should always give reasons for why our theorem is true. This theorem, there is a proof for it, believe me, there is, and I remember seeing it when I took advanced calculus back in the day, and it's complicated and it's way beyond our capabilities right now. So you're just going to have to believe me that those are really the only things that can go wrong, is the things that I showed you. You can have a jump or like an asymptote that can break things. Your function might not be continuous, or you can have weird stuff going on with asymptotes horizontally or open endpoints for open intervals, but that's really the only things that can go wrong. Okay, but we're not going to have a formal proof of this, unfortunately. It's a bit past what we want to get into. But yeah, so in the next video, we will talk about using the extreme value theorem to actually give us a method for finding global maxes and mins, and I will see you then.